Hello all, and welcome to the next session in the course Pre-MBA Statistics. So as you see in front of you, the topic for today's session and the next session is going to be hypothesis testing. So I'm very sure, almost 100% sure, that many of you might have heard about this term hypothesis testing. So we'll sort of elaborate the steps involved in hypothesis testing. We'll sort of go over some key definitions in the beginning and so on and so forth. So we started this week by discussing sampling distributions. Again, if you remember, I'll give you a quick refresher so that things are not disconnected at your end. So what do you mean by sampling distributions? We started with distributions like T and then chi-square, if you remember. And again, we sort of proposed some parameters for both these distributions. For example, the parameters for both T and chi-square are known as degrees of freedom. So something like Tn or chi-square n, etc. And the idea behind sampling distributions are all these distributions are sort of evolved, or rather sort of an extension of a normal distribution. So how do you arrive at, or how do you sort of derive a T distribution or chi-square, etc. And then the second session was mainly about confidence intervals, isn't it? So we started with the idea of estimation. Now again, estimation could be of two kinds. It could be point estimation or interval estimation. And then we spend some time in understanding a few ideas about point estimation. So imagine you have a parameter theta. Okay, so let's say if you bring in some practical data, and then you think that the practical data sort of behaves a particular distribution, let's say normal distribution. Now again, you look at the underlying parameters of the normal distribution, particularly mu and sigma square. But let's say in general, we can give a notation of theta. So theta is unknown. So what do? You have to estimate theta. Okay, so theta is a population parameter which has to be estimated from the underlying data or the underlying observations that you have. And then we sort of pinpointed to two kinds of estimators. So on one hand, you have a point estimator theta hat, and on the other hand, we sort of proposed an interval. So theta hat minus a, and then theta hat plus b, something like that. So you sort of create a symmetric interval. And how do you get hold of these a and b is the key question that we saw in the last session. Okay. Now, of course, I'll give you a simple example. If my theta happens to be nothing but the population mean mu, then naturally my theta hat has to be something like x bar. Okay, and then beginning or starting with x bar, then you sort of create an interval around x bar so that you get hold of a 100 into 1 minus alpha percent Ci confidence interval for theta. Okay, so again, a strong suggestion would be just before you start with the current session and the next session, just again go back couple of sessions, try to revise what we covered. We took up some examples also. If you remember, we took up example of insects, right? And then the idea was to create an interval for the lengths of insects and so on and so forth. Okay. Alright, now the idea is slightly different. We are going to test a hypothesis, okay, and hence the name hypothesis testing. Okay, so we'll see again, like I said, some definitions. We'll sort of create the null hypothesis, the alternative hypothesis, and then we'll sort of put forward some standard definitions and standard methodology. Alright, so in the beginning, what exactly do you mean by a hypothesis? So the first point sort of gives you or sort of defines a statistical hypothesis. So a statistical hypothesis is nothing but a claim about a population. Now again, when I say about a population, whether it is about a single parameter, the values of several parameters, or the form of an entire probability distribution. Okay. Now again, these three identities or these three ingredients sort of pinpoint to the behavior of a overall distribution or a overall population. So it could be a single parameter, let's say like mu. It could be several parameters, let's say mu comma sigma square collectively, or it could be the overall distribution, let's say normal or binomial, etc. Okay. But using any of these three or at least one of these three sort of characteristics, one can get hold of or one can realize the overall behavior of the population. So again, just to summarize, a hypothesis is certain claim about a population. So this term claim is sort of important. We're sort of claiming something about the population. So it might be about a single parameter, several parameters, or the form or the structure of the entire probability distribution. Okay. Secondly, a hypothesis test is an assessment of the evidence provided by a data set in favor of or against a hypothesis about a population. So let's say the moment you create a claim about a population parameter or a distribution, we have to somehow test it out. Okay, so claim is just an assumption. Now again, the idea again stems down to assuming that the population is unknown. So all these quantities, let's say mu, sigma square, etc., are unknown. So the moment you claim something about the parameters or the general population, you have to test it out. And this testing procedure is nothing but called as hypothesis test. Okay. So a hypothesis test is nothing but an assessment of the evidence provided by a data set in favor of or against a hypothesis about a population. Alright. Alright, now the most important idea is, again, like I said, some definitions to begin with. So we have two different kinds of hypotheses, so null and alternative. And again, I am very sure that you might have heard about all these terminologies. So null hypothesis, alternative hypotheses, etc. So what do you mean by that, and what exactly is the differentiating point between a null hypothesis and alternative hypothesis? So the first one, the null hypothesis, denoted by H naught or H0, is a null hypothesis, is nothing but the claim which is initially assumed to be true, or in other words, it's called as a prior belief. So let's say a simple example, we although have some examples down the line, but I'll give you a very simple example. Let's say the idea is to sort of find out the average height of all the students in your college. Okay. Again, the idea is to find out or gauge about the average height of all the students in the college. Okay. So one null hypothesis could be that, let's say you assume that the height is, let's say around the average height is 5 feet 5 inches. Okay. So immediately I can create my null hypothesis. I can write down mu equal to 5.5. Now again, why mu? Because you're concerned with finding the average height. Okay. And mu stands for the population mean. And how much do you assume that to be true? So you assume around 5.5 inches. Okay. Now on the other hand, so I can put this in the null hypothesis. On the other hand, let's say if you believe that the height exceeds 5.5 inches. Okay. So that part I can actually put in the alternative hypothesis. So mu exceeds 5.5. Alright. So if you assume that mu exceeds 5.5, you put that in the alternative. Null would be mu equals 5.5, and then you organize the testing procedure. Makes sense somewhat? So we'll see some examples, don't worry. But again, null hypothesis and alternative hypothesis, they have to be in line with whatever you assume. Okay. Now again, one claim throughout this entire course and much more standard assumption is that the null hypothesis you only have equal to sign. Okay. So null hypothesis only has equal to sign. It cannot have bigger than, less than, not equal to. So all these three other alternatives can come into play in the alternative hypothesis. Okay. So again, like I said, if your prior belief is that the height exceeds 5.5, okay. So think of a situation that you create a null hypothesis which is without any special effects. So put mu equal to 5.5, and the alternative you put mu bigger than 5.5. Make sense? So again, the null hypothesis is the claim which is initially assumed to be true, or the prior belief. On the other hand, the alternative hypothesis, denoted as HA, is the assertion that is contradictory to H naught. So if you assume that the height exceeds 5.5, then I can put null to be equal to 5.5, and then I can put alternative to be more than 5.5. Okay. Another example. So let's say a person wanted to check if a coin was fair. So very simple example. He tossed the coin 20 times and got 13 heads. Okay. So now the question is this evidence that the coin is fair? Now again, the idea here revolves not around some average, some variance, but a proportion. Okay. So let's say if you're tossing a coin 20 times and you're getting 13 heads, is this a fair enough evidence that the coin is fair? Okay. So my null hypothesis could be, so what do you mean by coin being fair? Coin being fair means if I denote P to be probability of heads, and naturally 1 minus P would be probability of tails, then I can put in the null hypothesis exactly that P equals 1/2. Alright, because for a coin to be fair, my P has to be 1/2, which is probability of getting a head, and similarly my 1 minus P, which is probability of getting a tail, is also 1/2. Okay. So very naturally I can put my null hypothesis to be P equal to 1/2. Now again, let's say if you want to check if the coin is biased or unbiased, a natural extension about the alternative hypothesis could be P is not equal to 1/2, isn't it? Now you're not concerned whether the coin is biased towards heads or biased towards tails. You simply want to check if the coin is biased or not biased. Make sense? So whatever the base assumption is, you always put that in the null hypothesis, and whatever you think or whatever you want to test for, that you put in the alternative. Make sense? So here in this case, my H naught would be P equal to 1/2, and my alternative would be P is not equal to 1/2. And again, what exactly is P here? So where P is a probability that the coin lands on head in a toss. There. Okay. So P equal to H is not correct. So P in fact is probability of getting a head. and 1 minus p is nothing but probability of getting a tails there. Alright. So, hopefully if you get the idea of null hypothesis and alternative, things would be slightly more clearer, because if you are testing any hypotheses, creating or writing down the null hypothesis and the alternative hypothesis is at the more important there. Alright, so one more example, a small yet another example. Let us say to test a manufacturing procedure, 500 items it produced were randomly sampled and 34 of them turned to be defective. So, again this is an entirely a question about a proportion and not some average or some variance, etc. Okay. So, you sample 500 items and then you find out that out of 500, 34 of them turned to be defective. Now, the key question is that is this evidence that the procedure has a defective rate lower than 10%? Okay. So, think for a minute and then structure the hypothesis in your mind. By the way, the answer is there in front of you. So, a natural extension to write down the null hypothesis could be p equal to 10%, which is 0.1. And since you think that the defective rate is less than 10%, I can write that down in the alternative. So, once you write down H naught and HA, then you can sort of proceed with the testing procedure. And what exactly is P here? So, P is nothing but the defective rate of the procedure here. Alright, now the key assumption is that once you write down H naught and HA, then if you directly jump to the conclusion of a test. So, how can you conclude something? Okay, so we will talk about that now. Now, the null hypothesis will be rejected in favor of the alternative only if the sample evidence suggests that H naught is false, isn't it? So, let us say, so how do you test it out? So, let us say once you create H naught and HA, there is a procedure, we will talk about that very soon. There is a fixed procedure as to how should you carry about the testing procedure or the testing process, okay? And the entire testing process revolves around the data set that you collect, alright, because again the key assumption is that the population is unknown. So, how do you sort of estimate the population? Always through the whatever data set or the set of observations you have collected, okay. Hence, the null hypothesis will be rejected in favor of the alternative. So, we will say that the null hypothesis is rejected in favor of the alternative only if the sample evidence suggests that H naught is false. Otherwise, we can't reject the null, okay. On the other hand, if the sample does not strongly contradict H naught, we will continue to believe in the plausibility of H naught, okay. Thus, to summarize, one can either reject the null or fail to reject the null. So, these are the two possibilities, isn't it. So, once you write down the null and the alternative hypothesis, depending on the testing procedure, depending on the sample evidence, etc., etc., I can either reject the null or fail to reject the null there, alright. So, these two are pretty standard conclusions that one can make from any hypothesis testing process, okay. So, I should write it down here that this is the, in fact, the concluding step or the final conclusion of the test there. Alright, so sort of how do you generalize this? So, now let us not get into, let us say, some p or some mu, some sigma square, but how do you sort of create a general procedure, okay. First step, like we discussed earlier, is identify suitable H naught HE, okay. So, the moment you get hold of or the moment you think that you have to test out a hypothesis testing procedure, the very first step is to identify some suitable null hypothesis and alternative hypothesis, okay. Generally, I will write down my null hypothesis to be something like this. So, theta equals theta naught. Now, again, what is theta here? So, theta is some general parameter. So, you are presenting a general scenario, okay. So, again theta could be mu, my theta could be sigma square, etc., etc., okay. But generally, I will keep H naught to be something like theta equals theta naught, and this you have seen in the couple of last examples we saw there, isn't it. So, p equal to 1/2 or p equal to 0.1. So, again in this case my theta is p, and what exactly is theta naught? So, theta naught is that value which is assumed to be true under the null. So, for example 1/2 or 0.1, etc., etc., okay. Or if you remember the heights example, the student's heights example, there we took mu to be 5.5, okay. So, in this case my theta is mu, my theta 0 or theta naught is 5.5, okay. Alright, so generally I will fix my H naught to be theta equal to theta naught, and then my alternative could be any of these three kinds, by the way. So, my one of the alternatives could be theta exceeds theta naught, or theta is less than theta naught, or theta is not equal to theta naught, okay. So, again what exactly is theta naught? The theta naught is called as a null value. So, again like I said, just to summarize, theta naught is nothing but that value which is assumed to be fixed or true under the null hypothesis only, okay. So, once you fix this theta naught, now again depending on what your assumption is or what you want to test for, I can actually keep my alternatives to be one of these three kinds. Okay. Now again this point is important, that the alternative cannot take all the three kinds, it has to be one particular kind, either the first one or the second one or the third one, depending on whatever you want to test for. Okay. So again, just to give you a quick example, so again in the heights example, you assume that my mu or the average height exceeded 5.5 there. So this belongs to the first category here. Okay. And if you remember the defective rate example, if you want to test for the defective rate is less than 10%, that falls in the second category, and so on and so forth. Okay. Alright, now the next very important procedure is, let's say you've written down H naught, HA, you know what you mean by null hypothesis, alternative, etc., etc. Now the second step in the testing process is, once you identify the null and the alternative, is to identify a test statistic. Okay. So we have a thing called as a test statistic. And what exactly is a test statistic? So again, if you remember, vaguely remember from the last session, we discussed what you mean by a statistic. Okay. So statistic is what? Statistic is nothing but a function of the sample data on which the decision is to be based. So here definition of a test statistic is nothing but a function of the observations or function of the sample data that you have collected on which the decision is to be based there. Okay. So very quick example, let's say you've collected these observations x1, x2 up to xn. Now can you pause the video and then try to tell me any function of these observations? So one example could be x bar. Alright. So in this case, x bar could be one possible test statistic, or some function of x bar could be one possible test statistic. So we'll specifically see down the line in this session and the next session as to how do you create that test statistic specifically. Okay. Anyways, but then the second step, once you identify H naught and HA, is to identify a suitable test statistic, which is nothing but a function of the sample data on which the decision is to be based. Then the third important point is, once you identify a test statistic, is to identify a rejection region. Now what do you mean by rejection region? So again, as the name suggests, rejection region is nothing but the set of all test statistic values where my null hypothesis will be rejected. Okay. So again, rejection region is what? The set of all possible test statistic values for which my null hypothesis H naught will be rejected. Now immediately I can sort of write down this very neat table here, isn't it? So now I will try to explain this very briefly. So the first column you see is reality. So what exactly is the truth? Okay. Now again, the reality can be one of H naught or HE. So either H naught is correct or HA is correct. Okay. So the first column is reality, and the first row gives you the result of the hypothesis test. So again, let's say, so H naught means what? The result stands for that the H naught is true, and this HA stands for the result means HA is true. Okay. Now, so I can get a grid of 2 by 2 exactly. So you see tick marks here and here, isn't it? You have a tick mark here and a tick mark here because the test suggests H naught and reality is H naught. So there is no error here, isn't it? Similarly, if the test suggests HA and the reality is HA, you are going good, isn't it? So you have tick marks here, there is no problem, but you have couple of errors on the off diagonal terms, isn't it? So if the test results in HA but then truth is H naught, which is this guy, so this is called as a type 1 error. You are making some error, right? Because the truth is H naught, but then the conclusion from the hypothesis test is HE. Okay. Similarly, the conclusion from the hypothesis test is H naught and the truth is HA, this is called as a type 2 error. Okay. So again, these are the only two kinds of errors that one can make in a hypothesis testing procedure. So you go by what is the truth and you go by what the conclusion is of the testing process or the hypothesis test, and if these two things are not matching, you are making some sort of an error there. Okay. So these are again standard definitions. We can either have type 1 error or type 2 error there. Now again, the two errors. So the first one, like I said, is type 1 error. Now probability of making a type 1 error is called as alpha, or rather is denoted by alpha. Okay. Now again, remember what exactly is type 1 error. I can actually write down type 1 error is rejecting the null given that the null is true. So this vertical line, if you remember conditional probability, this vertical line stands for that. Okay. So rejecting the null given that the null is true. So the truth is that the null is true, but the conclusion of the testing process is rejecting null. So you are making an error there. Okay. So this definition is called as a type 1 error, and probability of making that type 1 error is denoted by alpha. On the other hand, what is type 2 error? So type 2 error means not rejecting the null given that the alternative is true. So if the alternative is true, but you are still sticking with the null, you are making some error there. Okay, and this error is called as type 2 error. And then probability of type 2 error is called as beta. So you have two notations, alpha and beta. So probability of type 1 error is called as alpha, probability of type 2 error is called as beta. Okay. And thirdly, if you do 1 minus beta, so 1 minus beta is called as the power of the test. Okay. Now again, after seeing all these slides, I'll ask you a simple question. So if you are handling a testing process or hypothesis testing procedure or a problem, so what exactly should be your outlook, or what exactly should be the goal? So again, you can pause the video and try to answer this question. So your ultimate goal in any hypothesis testing problem should always be to reject the null. Okay. So again, if you go back to all the examples we discussed, so let's say if you think that the assumption is that the defective rate is less than 10%. Okay. So again, what you do in the null hypothesis, you put p equal to 0.1, in the alternative you put p to be less than 0.1. And if you assume that the defective rate is less than 10% indeed, then your goal or the outlook from the test should be to reject the null. Okay. And similarly, you can take hold of any other example and then cross check, isn't it? So you should always keep this in mind, that if you are creating a testing process, your goal should be always to reject the null. Now again, if the null is not rejected, well and good, but if the null is rejected, then you are kind of going with the assumption that you are making. Okay. Anyways, but then these two are the errors. So type 1 error, type 2 error, and 1 minus beta is called as the power of the test. Now surprisingly, we have a trade-off between alpha and beta. So we'll try to explain what exactly is a trade-off. So suppose an experiment and a sample size are fixed. So let's say if you have an experiment and a sample size, both are fixed, and then a test statistic is chosen. Okay. Then decreasing the rejection region results in a smaller value of alpha, while a larger value of beta for any particular parameter value consistent with HA. So you have a trade-off between alpha and beta. So what exactly is the trade-off? So again, I'll try to summarize this very briefly, that so the trade-off exactly is that if you try to minimize alpha, then the value of beta tries to increase. And similarly, if you try to minimize beta, the value of alpha tends to increase. And again, as you know that both alpha and beta are some errors, right? So you can't try to maximize some errors, isn't it? So the moment you try to minimize one of the errors, the other error jumps, kind of. So this is a trade-off. So then what do you think, how should you go about and then do the testing process? So the standard approach is hence to fix alpha. So I can sort of fix the probability of type 1 error. Okay. And by the way, this alpha has another alternative name called as significance level. And on top of that, if you again go back to the confidence interval session, we've been talking about 100 into 1 minus alpha percent Ci throughout, right? So this alpha is the same alpha that you see here. Okay. So again, if you remember, there in the confidence level section, we sort of fixed alpha to be a small number, is it? 1%, 5%, 10%. Similarly, 1 minus alpha would be large. Okay. So that alpha and this alpha both are the same. So alpha is called as a significance level. 1 minus alpha is called as a confidence level. Alright. Anyways, but then again, going back to the second point, a standard approach is hence to fix alpha and then try to minimize beta as much as possible. Okay. And then this is doable. So you fix alpha, you don't tamper with alpha anymore, you fix some number, again let's say 1%, 5% or 10%, and once you fix that value of alpha, then you try to minimize the other error as much as possible. Okay. So this is small trade-offs. You should always keep in mind that at the same time, I cannot try to minimize both the errors simultaneously. So again, if you try to minimize one of them, the other one should shoot up and vice versa. Alright, we'll take a small example, and then in this example, we try to create some rejection regions. Okay. So let's say again, if you go back to the coin toss example, these were my null hypotheses and the alternative. So H naught is P equal to 0.5, and then the alternative is P exceeds 0.5. Now again, why exactly are you keeping this alternative? So let's say you think that the coin is biased towards heads and you want to test it out. Okay. So biased towards heads means what? So if you denote P to be probability of heads, okay, so if you denote P to be small p to be probability of getting a head, then bias towards heads means P should be bigger than 0.5, which is exactly what you see in the alternative. Okay. So again, in the coin toss example, assume that these are the null and the alternative. Now a test statistic is what? So test statistic is nothing but number of heads in 20 tosses. So let's say if you toss the coin 20 times, I can look at how many times you are getting the heads, and that single number, which has to be a random variable by the way, would be nothing but my test statistic. Now, thirdly, assume that the rejection region is this guy. So, 13, 14, 15 all the way up to 20. So, what do you mean by this? So, rejection region means that if my x would take any of these values in this set, I will reject my null. Okay. So, again remember what do you mean by rejection region? So, rejection region is that set which amounts to rejecting the null hypothesis. Okay. So, you conduct the experiment, you toss the coin 20 times, and then if you find out that the number of heads is at least 13 as per the rejection region, then you reject the null. And again, rejecting the null means what? Rejecting the null in this case means that the coin is indeed biased towards heads. Okay. So, now if you try to connect the dots, it will come to a much more clearer sort of an expression that you write down H naught HA, you write down a test statistic, you write down the rejection region, you conduct the test, and based on the rejection region you find out whether to reject the null or go with the alternative. Alright, now we will try to find out the values of alpha and beta quickly. Okay, so how can I do it? So, let us say under H naught, okay, my x follows a binomial distribution with parameters 20 and 1/2. Okay. Now, all these things are kind of standard. So, you are tossing a coin 20 times, and what is x? X is the number of times you are getting heads. So wouldn't that be a binomial distribution? It will be a binomial distribution where n is 20 and probability of getting a heads is 0.5. Okay. So, this fact is fixed. So, under my null hypothesis, x follows binomial 20 comma 0.5. Now, again, how do you find out alpha? So, you have to go by the definition. So, alpha is probability of type 1 error, which is probability of rejecting the null given that the null is true. Now, from the last slide, when would you reject the null? So, simple question. So, when would you reject the null? You will reject the null, like I said, when x is at least 13. Okay. And given that the null is true means x takes this distribution, is it? Now, this is a very simple problem. So, assuming x is binomial 20 comma 0.5, what is the probability that x exceeds 13? I can do this calculation or do the math in Excel, or I can pull up a binomial table, and it so turns out that the answer is 0.132, which means that the probability of incorrect rejection of the null is 13%. Okay. Now, on the other hand, we will quickly do type 2 error. Now, assume that p is indeed 0.6. Okay. So, assume that p is 0.6, then can you find out the value of beta? Indeed. So, what is beta? Beta is probability of type 2 error, which is probability of not rejecting null given that the alternative is true. So, again, when would you not reject the null? You will not reject the null when x is less than equal to 12, is it? You will reject the null when x is at least 13, you will not reject the null when x is less than equal to 12. And given that the alternative is true, so under the alternative, what is the distribution x takes? So, under the alternative, x takes binomial distribution with parameters 20 comma 0.6, because you are assuming p to be 0.6 here. Again, a simple math, and the answer is 0.584. Thus, our assumption is that for every value of p, there is in fact a different value of beta. So, if I change this value from 0.6 to 0.7 or 0.8, I will in fact get a different value of beta. Okay. So, this is one set of problems. So, if somebody gives you a rejection region, how do you find out alpha and how do you find out beta? So, these are one kind of problems. Now, in the next session, we will focus more on, you might have heard about tests such as Z test, T test, etc. So, we will focus more on some specific problems under a normal distribution only. Okay. And then of course, the last session would be again to sort of combine all the ideas, take some examples, solve them, conclude some testing processes, create some intervals, etc. Okay. Thank you.